Scaling a vertical surface presents a direct physics problem. To overcome gravity, a climber needs immense static normal force to hold tight to the wall, yet forward motion requires dynamic, low-friction sliding. Biology manages these conflicting physical requirements. In the streams of Hawaii, the Sisyopterus goby inches its way up sheer, wet waterfalls. This capability follows a specific physical transformation. During post-larval development, the goby undergoes a rapid cranial metamorphosis that reallocates its premaxilla-maxilla complex, the bones of the upper jaw. This restructuring converts the feeding mechanism into a powerful oral sucker. It generates suction force 4.3 times the fish's own body weight against gravity. The ascent relies on a precise kinematic sequence. Using a 4-bar cranial linkage, the goby alternates its anchor points between this oral sucker and its fused pelvic fins. The fish bypasses conflicting physical forces through highly sequenced dynamic changes to its morphology. Translating this organic, dual anchor system into synthetic architecture is the core challenge of soft robotics. This design replaces biological tissue with a dielectric elastomer actuator, or DEA, and substitutes iological suction with variable electroadhesion. This sequence of photos shows the result: a tethered soft robot executing a stable vertical climb. Tracking the vertical displacement between frames establishes a climbing speed of 0.75 body lengths per second. The engineering relies on mirroring the mathematical control logic of the goby's alternating gait. This diagram of the robot's body isolates the DEA that acts as the synthetic muscle. The material stack consists of a biaxially pre-stretched VHB 4910 membrane sandwiched between two compliant cardon grease electrodes. This 3D render shows the baseline mechanical state. When the pre-stretched membrane is relaxed, the tension forces the rigid acrylic frame to buckle into an arched saddle shape. Applying a specific voltage, designated as VA, polarizes the carbon electrodes. This generates electrostatic pressure that compresses the elastomer membrane. This schematic shows the macro deformation. Electrostatic compression forces the saddle to flatten, extending the footprint from the blue to red state. Removing that voltage eliminates the pressure. The elastic recovery contracts the body back to its original geometry. The DEA converts discrete electrical inputs into linear displacement, functioning as a programmable muscle. To climb, the robot requires feet that replicate the goby's oral and pelvic suction. Each pad is constructed from interdigitated concentric copper electrodes, insulated by thin polyamide layers. Electroadhesive grip follows a specific equation. When voltage is applied to the foot, the perpendicular normal force scales with the square of that applied voltage. Fn equals K times Vf squared. That normal force provides the required climbing friction. The tangential force, which resists the downward pull of gravity, is calculated by multiplying the normal force by the effective friction coefficient of the surface. This creates a binary constraint for locomotion. The system uses a high voltage state for the anchoring foot and a low voltage state for the foot that must slide forward. Electroadhesion allows a single component to toggle instantly between absolute grip and free sliding release. Movement depends on phase locking the muscle's expansion to the on and off states of the electroadhesive feet. In this sequence, the initial step starts with the front foot at a low voltage slip state and the rear foot at a high voltage anchor state. As the muscle voltage increases, the actuator extends. Because the rear foot is anchored, the expansion pushes the sliding front foot upward. At the midpoint, the states switch. The front foot snaps to high voltage to anchor, while the rear foot drops to a low voltage. As the muscle voltage drops to zero, the material's elastic recovery contracts the body, pulling the sliding rear foot and the payload upward. Vertical climbing relies on a hyper-precise, repeating loop of discrete electromechanical state switches. Real-world deployment requires the system to maintain this synchronized loop across various surface textures. The robot adapts to glass, paper, and raw wood by adjusting the voltage baseline applied to the feet. This deployment is governed by a mechanical boundary condition, the maximum blocking force of the actuator. The tangential adhesion force of the anchored foot must remain greater than the blocking force generated by the muscle's expansion. That intersection represents the failure threshold. If the muscle pushes harder than the foot's grip, the anchor shears off, resulting in a critical failure. Vertical mobility is dependent on ensuring the adhesive holding capacity outscales the muscle's maximum output. This architecture also provides secondary benefits when navigating complex planar geometries. Soft systems lack the fixed joints or rigid transmission linkages found in traditional climbing robots. This allows the robot to passively deform its body, scaling its height down by 58% to navigate underneath a low barrier. Translating biological kinematics into soft architectures creates machines that inherit the morphological adaptability of the organisms they mimic.